Hi, everyone. Thanks for being here today. I'm going to tell you about inertial appendages, but first, I want to start with a question kind of about our whole session. Like, why do we do bioinspired design? And in my lab, we study animals, right? So we do biology research. My background is in biology. We design bioinspired robots, but we also build robots to further the study of biology. So here are some examples that you might be familiar with. You're here in this session, so you're probably familiar with some of these. Here are some examples from my esteemed colleagues in this session, right? So we've got a beetle-inspired drone riding, microbe-inspired flagellar locomotion, eel-inspired origami, and our conference co-chair has actually made a bat-inspired drone. My lab is presenting a brittle star-inspired robot tomorrow, so please come see us. But I also want to highlight that robots can give back to biology, even very simple robots. So to study the parental care of poison dart frogs, Tony Chen made a robotic tadpole that begs its parents for attention. And to study sage grouse lecking behaviors, Gail Petrocelli made taxidermy fembots to watch the male performances. So here's a video from that female point of view. It's quite appealing, isn't it? So these are two relatively simple robots, but they really do help us understand science and biology better. So today I'm going to tell you the story of inertial appendages that actually spans my entire career, but I want you to think about it in terms of what elements are biology for robots and what elements are robots for biology. So when I was an undergrad working with Bob Full at Berkeley, I was recording lizard locomotion for my biomechanics class. And by accident, I actually discovered that lizards use their tails to compensate for over-rotation in body angle during leaping. So the tail can help maintain or even increase pitch or decrease when they overshoot. And we hypothesized why this was happening. You know, is it just a coincidence that the tail is moving, or is there actually some mechanism here? So we hypothesize that this is because your total system angular momentum has to stay constant while you're in the air. So your body angular velocity is your tail, your total angular momentum minus the tail angular velocity times a constant. And this constant is proportional to the tail moment of inertia to the body moment of inertia. And so we wanted to test how general this could be, so we built a tailed robot. This tailbot was a modified RC car that had a gyroscope to sense angular velocity, as well as PD control of a carbon fiber tail with a brass weight. So we tested this car by driving it off a ramp with the controller off. It does quite poorly, it nosedives, so don't drive a car off of a ramp unless it has a tail that is actively controlled, because when you turn that controller on, it was able to maintain body pitch, land, and even keep driving across the room. And so when we compared these robots to the lizards, we found that we could change the morphology of this robot to get a wide range of effectiveness of the tail and actually outperform the lizard. So this was really great. It helped demonstrate our hypothesis was generalizable, but it also conferred a new capability to robots. So inertially maneuvering tails, inertial appendages, are now common in robots. So we've got tails that help you jump, tails that help wheeled robots turn and legged robots turn, tails that can help you recover from perturbation, and tails that can even help you perform a barrel roll. So note that these are all rigid link tails that all move in a planar rotation. And some of our work also looked at other biological systems. So velociraptors, they can outperform lizards, but the robots can still be better. Some of our colleagues worked on praying mantises, hawk moths, and bats. And these all have very chunky, heavy inertial appendages with planar rotation. And so this was really cool, but then I went on to do my PhD in another lab on the biomechanics and evolution of bipedal hopping rodents called jerboas. These are really agile animals, but they have very thin tails. And actually, mammal tails in general are thinner than lizard tails because lizards have muscles that go all the way down their tails. Whereas mammals, we have our tails in our torso. All of our muscles are in our torso, and they extend to the tail vertebrae by these really long tendons. And so mammal tails are a great inspiration for tendon-driven continuum robots. So I wanted to know, can the jerboa use its tail as an inertial appendage? So I got out my nifty lizard-based moment of inertia ratio metric. For reference, the lizards are about 0.25 or 0.275, and the jerboa was 0.06, so terrible, right? I discussed this with my colleagues, and we agreed probably the jerboas can't use their tails for inertial appendages. So for 10 years, I did other things. I did a bunch of research on jerboa evolution and biomechanics. I don't have time to talk about it today, but if you're interested, here are some references. But while I was doing these other studies, I kept getting videos like this, where you can see tail motion and you can see body rotation. How do we explain this? So my first PhD student was like, I really think that we need to finally study this. There are some big differences here between the lizard and the mammal here, right? So these tails are curving in multiple directions along the length of the tail, and it's rotating in 3D. So to really understand what's going on here, we need a way to find the maximum effectiveness of inertial appendages that are vastly different in morphology and motion. And one of the things we think here is that the curvature is really important, and curvature is determined by the bones, right? The bones tell you what curvature you can and cannot do. So my first PhD student, Shunfu, decided to perform simulations of robotic tails in which each joint is actuated in 3D space. The torso cannot move on its own. It has to be rotated by the tail motion. And the tails all share the same total mass and total length, but they differ in link number. He formulated it as an optimization problem, so we can measure maximum tail effectiveness by how close you can get to a very challenging tail or body rotation trajectory. So we've had a few different constraints, like your total maximum total control effort cannot change. So even if you evolve more tail joints, you keep the same brain power to control the tail. And so we formulated this as a Hermite-Simpson collocation problem, and we varied our initial conditions. What did we find? Well, the jointed tails really do outperform that single link tail, and the optimal trajectories had 3D curvature. And so this really does tell us that these two features help a low inertia tail generate more angular momentum than we would have predicted if it was just planar. So more tail links is better, and optimal tail trajectories have multiple curves. While we were doing this research, we were taking a look at mammal bones more broadly with our collaborators, Kim Cooper and Carrie Weber, who are developmental biologists. And we found that the length of the bones is not constant along the tail. Your first vertebrae are short, then they get very long, and then they get very short again. And so we wondered, is this variability an evolutionary holdover, like it's just leftover baggage, or is there a function to this? So we went back to our optimization problem, and instead of just having uniform bones, we asked the optimization problem to vary the lengths of each link and find the optimal pattern of link lengths for a tail. And what we found is that if we allowed the link lengths to vary, these tails outperformed the uniform link tails every time. So what are those optimal link lengths? Well, they always start out short, they get a little longer, and then once you are able to get past that mid-region, they get shorter again. And this is great, because it was a pattern that we saw in the mammals. So if you look at mouse-related animals, they also have kind of a crescendo and decrescendo. But if you look at animals, these mammals that use their tails as inertial appendages, they have a huge crescendo and decrescendo. And so our simulation shows that this is actually giving a function. But there are also these big differences between the simulation and biology, right? So the mammals can have like 35 tailbones and dozens of tail muscles. And do we really need all that? Well, let's take a look at our results again. We see that we have diminishing returns. So when you have 4, 5, or 6 tail lengths, you don't actually get that much more control, not much more inertial maneuvering, right? And it turns out that the control effort constraint, these are all different control parameters, each physical parameters. The one on the very right shows that the control effort is near the limit during the entire trajectory. And so it's constraining the complexity of the control input. How does biology get around that? Well, one way that people have been looking at musculoskeletal control is by building these digital twins of musculoskeletal anatomy called OpenSim models, and then simulating the kinematics and/or dynamics resulting from different control inputs. And there are a ton of really awesome animal models, but it turns out that every animal model is missing a tail. And in fact, tails are left out of most anatomical studies. So if you look up mammal morphology and musculature, they never have the tail. And so we're building the first OpenSim tail model, and we had to actually construct new modeling tools to do this. And when we're done, we should be able to understand how mammals can generate these complex tail shapes and motions without greatly enhancing their neural control architecture. But if we want to reduce complexity, where do we start? Well, my postdoc Jerry is doing a broad comparative study of mammal tail muscle tendon anatomy. She's dissected all of these animals, and what we're looking at is when distantly related animals share the same function, shared features are likely functional. And in closely related animals that differ in function, shared features are likely non-functional and can be trimmed out to reduce complexity. So based on what we're learning from these dissections, my PhD student Maggie is building a modular tail robot where we can set the tendons, the joint stiffnesses, and the bone lengths to match living animals, extinct animals, and theoretical morphologies that have never existed naturally. And then we'll empirically determine their functional performance at a bunch of different tail tasks. So this is ongoing research, so stay tuned for more from our lab soon. But I wanted to end it on what we've learned so far about inertial appendages, and this applies to both natural as well as robotic appendages. First, swing something heavy if you can, right? You want to have a high moment of inertia. But if you have to be light, increase the number of joints you have for a given length. Joints should crescendo and then decrescendo in length, but you probably don't need to precisely control each joint. All right, that's what we know so far, and I'm excited to do more about this. I'd like to thank all of these groups, many of whom donated specimens to our research studies. So thank you very much.
Thank you very much, very interesting. Any question? You are shy. Okay. No, it's a fake question. No, my point is actually related to the relation with the material, because with the OpenSim, you're going to have a generalized approach virtually, including maybe the possibility of investigating animals with a tail in water even. Could you comment on this, how powerful the tool would be also for engineering applications?
Yeah, so
maybe, yeah, good, yeah.
So this approach, this like comparative approach, has been demonstrated to work really well for a variety of different biomechanical tasks. And so we're really interested in kind of the tail as an inertial appendage right now. But this whole field of functional morphology actually helps us understand what are the morphological features that confer different functions. And there are studies across the entire body and across all species.
That's really fascinating. Thank you very much.